Hey, physical science kids, Mr. Tima here, going to talk to you about nuclear chemistry. Now, these notes are going to be broken up into parts. This first one is alpha and beta decay, or part 1, nuclear chemistry, part 1. Now, some of the biggest areas that we see nuclear chemistry to the average person is in our military vehicles, like aircraft carriers, nuclear subs, stuff like this, and in power plants. We actually have two or three, I can't quite remember off the top of my head, nuclear power plants in Ohio. One is down by Cincinnati and the other are up by Lake Erie. Okay? So remember the nucleus, again, it all goes around the nucleus, and just remember that we need to know these terms like atomic symbol, mass numbers, and atomic number. And remember, sometimes depending on how we write this, they can look different. Like on the periodic table, remember, the atomic number tends to be on the top and the mass number tends to be on the bottom. But back to nuclear, remember, the smaller number is always going to be the atomic number, the larger number is always going to be the mass. And sometimes when we refer to the atom in nuclear chemistry, we tend to use the words like nucleon or the nucleus because we're talking about the whole atom itself. We're not so much worried about individual parts, but the whole thing as itself. Again, isotopes. This is something that you were tested on, and you got to make sure that you know what an isotope is. But remember, it's atoms that are the same element, which means they have the same number of protons, but they have different. But the mass is different due to the number of neutrons. Okay, so again, like uranium, which is something you're going to have to start looking at. Which uranium, the atomic number, or excuse me, the atomic symbol for uranium is U. Okay. Which is, if you look at the periodic table, atomic number 92, okay? So these all have 92 protons, okay? But they have different amounts of neutrons. And remember, this is not the number of neutrons, but these are the mass numbers, okay? And remember, to get the amount of neutrons, we take the mass numbers and we subtract the number of protons to get our new mass numbers. Our number of neutrons, sorry about that. Okay, so just remembering this. So we would call this uranium-234, uranium-235, and uranium-238. All right, so what is the word radioactivity? Well, radioactivity means there's an emission of high energy radiation or particles from the nucleus. Okay? There are several ways that these nucleus can decay from different nuclides, and we're going to talk about those right now. The first one is called alpha decay. Okay, it is the first radiation that you have to know, and you're going to have to know 3 of them, but this is the first one, alpha decay. It's the least penetrating. It's the largest and slowest form of radiation. If, let's say, I had an alpha ray gun, and I held it up to you and I was going to fire and hit you with alpha particles, it's really easy to stop it. It can be stopped by a piece of paper. And remember, paper is not as dense as your skin, so that's why it just bounces off our skin. The only way it can get inside of you is it could kill you if it's released inside your body, because it can't get out of your body. It kind of bounces around in there. Back in the day, Fidel Castro, who was the dictator of Cuba, they actually tried to kill him by putting radioactive particles in his food, actually a milkshake, okay? But when we say alpha particle, we literally mean an alpha particle literally is a helium nucleus, okay? It is like not all heliums are alpha particles, but an alpha particle is a helium. Okay, literally meaning that there is this radioactive helium that shoots off. It literally goes and it shoots off the atom. Okay, and that literally means if we say alpha particle, we mean helium. So what's kind of nice is we have our symbol here, and the alpha particle is this symbol here. Right here, it kind of looks like a fish. Kind of looks like a little fish dancing around, swimming around. So for example, if we had uranium-238, okay, and we said it underwent an alpha decay, we always know that one of the particles on the other side, and remember, This is the reactants and this is the product. So we know that when this splits, when this uranium splits into the two things it's going to become, well, what is it going to become? We know one of the particles is always going to be this alpha particle, 4,2He. And then we're going to have to try to figure out what the mystery element, or what did the uranium turn into? Well, it's kind of easy. If you think about it, the total number of protons has to be 92. Well, if 2 of them are occupied by this helium, how many are left? 90. Same thing with the mass number. Look, if 4 of them were used up by the helium and the total is 238, then how many are left over? 234. If you look at the periodic table, this number really doesn't matter because that can be different on the periodic table. But this number, the atomic number, remember, always tells us what it is. And if you look at that, you find Th, which is thorium. And remember, those are down in the rare earth metals, all the way at the bottom chunk. So let's practice that really quick. Take a second, pause the video, and see if you can figure these out. I'll give you a hint real quick. And it doesn't matter where you write these. Okay, you could have either written it here or you could have written it here because it's addition, right? It doesn't matter. But I'm just going to write them right here. 4,2He, because it's alpha. If it's alpha decay, then we're always going to write 4,2He. It's kind of a giveaway. Since it's alpha, we know that 4,2He has to be there. All right, pause if you need to, see if you can figure out the mystery elements. All right, so the question is, we have to figure out what is our mystery element. So if we look at this top one, this is plutonium. If we look up there, we say if the total is 94. Well, what plus 2 gets me 94? Well, that'd be 92. What plus 4 gets me 244? Well, that's 240. And now, remember, I look at the atomic number. I don't look at the mass number, because depending on the averages, it could be different, all right? But I look at the atomic number, and I go up to the periodic table all the way down at the bottom, and I see 92 is uranium. So this would be uranium-240. All right, going down to the bottom, same idea. What plus 2 gets me 90? That's 88. What plus 4 gets me 234? So that's 230, sorry. Now we look at the atomic number. We look up there and we find 88, which is not radon, it's radium, okay, which is Ra. Okay? Again, if you have questions on how to do this, make sure that you ask me. Moving on, we're going on to beta. Now, each time we go up, it gets a little bit more dangerous. So beta decay, okay, and I'm going to walk you through this, but it's kind of complicated. If you imagine there's an atom, okay, and the atom kind of allows, okay, I'm going to back that up. If the atom kind of allows a neutron to kind of bubble up to the surface, and think about it, a neutron really is neutral because it's kind of composed of an electron, and it's kind of at the same time fundamentally like a proton added together. Remember, if these two added together, they make this neutron, okay? So what happens is a neutron kind of goes to the surface, and this all takes less than a nanosecond, and it can't decide what it wants to be. So the electron says, I'm out of here, okay? The electron says, that's not drawing really well. Let me try that again. Okay, the electron says, I'm out of here, and he goes, I'm out of town, see ya, I'm out of here. All right, and he leaves. But the proton gets scared, and he goes back to the atom. Okay, and he goes back to the atom. So once again, let's just walk through that real quick. Neutron kind of comes to the surface, kind of exists as both an electron and a proton. The electron says, I'm out of here. and the proton goes back inside the atom. Think about what that means. That means we lost a charge, but did we lose mass? No, because electrons don't have masses that we worry about. The proton goes back in. So even though we kind of lost the mass of the neutron, we pick up that mass, so the mass doesn't change. But the number of protons change. And we'll see this down below. So what I just told you is kind of written right here, okay? What's really important to know is it's more penetrating and much more faster than alpha decays. So if I had my beta decay gun, if you held up a piece of paper, it would go through the piece of paper. Now you need to use like aluminum foil, a piece of aluminum foil. Sometimes you'll see kind of people that you see in movies and stuff wear like aluminum foil hats. Well, that's because they're trying to stop like beta decay. So a beta particle, we write a B. So you can either see it written like this, but in this class we're going to see it written like this a lot, which says E0 negative 1. And that negative 1 is important because of the math part of it, like we talked about. Okay? So for example, if we have iodine 131 and it decays, beta decay, and sometimes we like to write that on here so we know that it's going through a beta. And we're trying to find this mystery element that you can already see here because we've already done it. But we would write 0, negative 1e. And if you think about it, we're doing the same math. 131, so what plus 0 gets me 131? Well, 131. And that makes sense because like we said, the mass isn't going to change. We kind of lose a neutron when we pick up a proton. They both have a mass of 1. Okay? But the atomic number is going to change. And the atomic number is actually going to get bigger. And you say, well, it says minus 1 here. How's it going to get bigger? Well, look, if we start with 53, what plus a negative 1 or what minus 1 is going to get me 53? Well, that's 54. And then again, we look at the periodic table to get this. I know it might be a little confusing. Let's work through a couple examples and see. All right? I'm going to do the first one with you right away, and then I'll take a break and you can see if you can do the bottom one. Again, since it's a beta decay, we know that beta decay literally means 0, negative 1e. So we're literally going to write that, 0, negative 1e, always, because it's beta. When it was alpha, it was 4,2he. Now it's 0, negative 1e, because it's beta. Okay? What mystery plus 0 gets me 84? Well, that's 84. 84 plus 0 gets me 84. What plus a negative 1 or what minus 1 gets me 35? Well, that's 36. Then I go to the periodic table, I look at the atomic number of 36, and I write down the example, the answer of krypton. Take a second, see if you can do the next one. See if you can do the next one. Hint, make sure you always start with what you're given, which is that it's a beta. So we know, since it's a beta, that it's 0, negative 1. What plus 0 gets me 234? 234. What plus a negative 1 or what minus 1 gets me 90? That's 91. If I look at the periodic table and I find number 1, or 91, I know that that's PA. Again, these are only going to get easier with practice, and we're definitely going to do that. The last one we need to talk about is gamma emission. Gamma emission. All right, now gamma has no mass and no charge, so there's no math involved with this. It travels at the speed of light. It's super, super powerful. Only lead and concrete can be used as barriers. So this is like what comes out of nuclear weapons. This is the big dangerous ones. You see this a lot in superhero movies. Like the Fantastic Four was hit by gamma emissions because it like changed all their cellular stuff. All right. The symbol for gamma is kind of like a diving fish. Okay, it's right here. And notice the math of it's 0, 0, so you don't need to worry about it. So if we were to do an example, if we were to say like carbon 6, or we'll go carbon 16, whatever, would go through a gamma, you would literally write 0, 0 gamma plus 6, oh goodness gracious, sorry, plus 16 carbon over 6, because nothing would change because of the 0, 0. All right? A term that we need to know is the word transmutation. Okay? Literally from Latin, the word trans means changing, which you've probably heard that term before, and mutation. Okay? I'm sorry, let me back up there. I messed that up. Let me back that up here. Trans, which means like to process. Okay, it's the process, and mutation, if you think of like movies like X-Men and stuff, that means that there's a process of change. Okay, mutation is the word for change. So it is the process of changing one element to another through nuclear decay. Well, think about that. Of the three that we just did, alpha, beta, and gamma, which ones actually change the element? The element that we started with to the element that it went to. Well, think about that. Which ones did that? Well, isotopes were given off in alpha and beta. Okay, think about it. Alpha, 4,2-HE, was given off and you changed the other element. Beta, 0, -1, changed the element. But gamma, nothing changes, right? So transmutation only happens when it goes through an alpha or a beta. All right? I'm not going to go through every one of these slides, but I want to just highlight that if you ever looked at the periodic table, you might have been sitting there going, wait a minute. I've always noticed this thing, like I've always noticed that, like helium, there's 2 protons and neutrons. Boron, 5 and 5. Carbon, 6 and 6. Nitrogen, 7 and 7. Okay? And if you were to look at that kind of 1-to-1 ratio happens a lot. But like if you go to like 50, okay, if you go to element 50, SN, it has a mass number of 119. But it has an atomic number of 50. If it was 1-to-1 the whole time, 50 plus 50 would be 100. Okay, but this isn't 100, it's 119. It actually has 19 more neutrons than it should have. It even gets worse as you get all the way up into here, as you start getting up higher and higher, like element 100. Element 100, okay, is FM, which is fermium, okay, and it has an atomic number of 100, so you would think that its mass number would be 200. Well, it's not 200. It's actually 257. It has 57 more neutrons than it should have. Well, why is that? Because neutrons, the elements, want to pull themselves apart. So below 20 and lower, they're about 1-to-1 ratio. But as they get bigger, the nucleus has to add neutrons to stabilize it. And that's why we call that the belt of stability. It is stabilizing the atoms. Neutrons stabilize. Okay? And the reason they stabilize is you have to think of it as like there's all these protons and there's all these electrons, and they don't like each other. It's like you and your brother and sister in the back seat. So what do you do on car trips? Well, when we were young, we used to stack pillows, or we'd put games or something in between us, okay? Well, those things that are in between, those are the neutrons, okay? So they're kind of like the pillows in the back seat that stabilize, okay? So again, and then the last thing I just want to talk about is notice things don't just go alpha, 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 beta, 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 beta. If you actually look at this, okay, this would be like an alpha decay. Then beta, alpha, beta, beta. Alpha, 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 beta, beta, alpha, beta, beta, alpha. Okay, so things can go through different decays. Okay, alpha, and these are betas, right? Okay, then we go alpha, 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 alpha. Okay, so just know that there are certain patterns that they follow, but they're not all consistent. Okay, that's where we're going to stop for today. This has been part 1. Make sure that if you have questions, and this isn't easy stuff, make sure you ask. Have a great day. Mr. Tima out.